Hi everyone. So in this video we are going to study the concept of delay only, but before that we will see a very interesting concept of universal gate. So what is a universal gate? I told you. So that universal particular gate is enough to implement any boolean expression. So I told you NAND gate is a universal gate. Then from the NAND gate we implemented NOT gate, AND gate, OR gate, NOR gate, NAND gate itself, then XOR gate and any kind of boolean expression, right? So NAND gate was alone enough to implement any boolean function. Similarly, NOR gate was also alone enough to implement any boolean expression. So this is what we mean by universal gate. Now the question is, are there only two universal gate? So fundamentally your answer should be generally there are only two universal gates. So what you will say if this question is asked to you, are there only two universal gates? So you will say generally there are only two universal gate, which are NAND gate and NOR gate. But this but if any logic circuit can give you AND or one of these AND or one of these AND or AND NOT. Look, what you need, AND plus NOT. So NOT should be written in capital. AND plus NOT or plus NOT. So if any logic circuit can give you AND or and NOT both together, then the circuit can be used as universal gate with the condition that 1 and 0 are present. Basically, high voltage and low voltage should be present. You might not be able to understand this. Let's understand with an example. So here what I have written, NAND gate alone is enough to implement any boolean function. NOR gate is also alone enough to implement any boolean function. AND plus NOT, that is also alone enough to implement any boolean expression. OR plus NOT, if two gates are given, then also they are enough to implement any boolean expression. AND plus OR plus NOT, they are also enough to implement any boolean expression. Now this gate is given, that is A bar B. This gate is given to me, A bar B. Now my question is whether it is a universal gate or not. Universal gate or not. I have a gate which can implement this function A bar B. That means what is the gate? This is the gate. This is the gate, right? Can it implement any boolean expression? That we need to know. Okay. Now what will be my target? If from this gate, if I can get OR gate, AND gate and NOT gate, if I can get these three, that means I can implement any boolean expression. Say yes or no. My target will be to get these three. That's it. Or what could be my target? That I can make NAND gate from here or NOR gate from here. If I am able to make NAND gate or NOR gate from here, then my task is done. So here I will try to make NAND gate from here, or all the gates I will try to make. So first let's try to make NOT gate. From here let's first try to make NOT gate. How will I make NOT gate? What I will do, I will pick the same. This is your A, and here I will keep 1. So what will be the output? Y. That would be, if this is A, this will be A bar. So A bar into 1. So Y will be A bar. That's it. This is the output. What is this? This is a NOT gate. Now let's try next. What I should try? I should try making AND gate. Let's try making AND gate. So what AND gate will do? AND gate will do AB, right? So first I will use this inverter. I will put A here and get 1 here. So from here what I will get? A bar into 1, that would be A bar. Then here I will go A bar, and here I will put B. So what I am getting? Here I will get A into B, y is equals to A into B. So what I have got? AND gate I have got. NOT gate I have got. What else I should try? OR gate. OR gate. So for OR gate, what you need? OR gate. For OR gate, you need A plus B. A plus B. Or I can say I can take double bar here. What if I take double bar? I can say I need A bar dot B bar bar. This is what I need. I can say that, right? So what I will do? First I will take the bar. First I will take the bar of B. First I will take the bar of B. So here I am getting, this is B bar. B bar into 1 would be B bar. So here I am getting B bar. And then here I will take A. So A bar into B bar. What I will get here? A bar into B bar. A bar into B bar. And then another inverter I will have. Here I will have another inverter. So what I am getting? So this is my output. A bar B bar bar, and here I will put 1. So my output will be A bar B bar bar, and that would be A plus B. So I have got OR gate, I have got AND gate, I have got NOT gate. If I need to make NAND, I can easily make NAND. If I need to make NAND, how will I make NAND? I will pick this one, and simply I will add an inverter. That's it. This Y is equals to AB is already there, and then after that I just need to add an inverter. And how will I add an inverter? This is a simple inverter is there. So if I am able to make a NAND gate, then from NAND gate I can implement anything. Any single thing I can implement from the NAND gate. So that's it. This I am having. This I will put as 1. This will be my AB bar. Well and good. Very easy. So if I am able to implement NAND gate, then it can implement anything. Can implement any Boolean expression. Implement any Boolean expression. So that's it. In that manner, you will be able to proceed. Okay. From NOR gate also you can make. How will you make NOR gate? OR gate is already there. Just add an inverter. OR gate is already there. A plus B is already there. Just add one more inverter there. That's it. That is your target. Or here also you are getting, no? This is your NOR gate. Yeah, this is the NOR gate. This much portion is NOR gate. This is your NOR gate. NOR. Because it is B bar into A bar. B bar into A bar will be A plus B whole bar. This is your NOR gate. So they can implement any Boolean expression. So my target was only to implement one of the universal gate. If you are able to implement one of the universal gate, then you can implement any Boolean expression. So what did I tell you? AND gate plus NOT gate. If both of the operation you can get, then they are more than enough to implement any Boolean expression. Or if you are having OR gate plus NOT gate, then they are more than enough to implement any Boolean expression. Same goes with this one. A bar plus B. A bar plus B. A bar plus B. So this is up to you. This is up to you. You can implement anything. What I will do, I will implement only NOR function. NOR should I implement? Okay, I can implement NOR. So what I will do, first I will make an inverter. Yeah. Okay. So my target is to implement NOR now. So first I will make an inverter. This is the logic gate I am having. This is A, this is B. Instead of B, I will put 0. So A bar plus 0 will be A bar only. So this I am getting as A bar. So A bar goes here. And then inverter comes. So it will be A. And this will be B. So from here I am getting A plus B. So this I will get as A plus B. Here it would be A plus B bar. A plus B bar. And then I will put 0 here. A plus B. I need A plus B bar. So A plus B bar here it will be. And then there to go. So here I am getting A plus B bar. Basically this was an inverter. This is the response of an inverter. So in one logic circuit only you can see 3 logic circuits there. And this, what is this? This is A plus B. This is A plus B. So this is a OR gate. And finally you can see NOR gate. So if you are having NOR gate, that means you can implement any Boolean expression. So this is also a universal gate. So these are the examples. So if you think that you need 3 gates, then you are thinking wrong. You need only 2 gates. Because in your chip, in your IC, there will be plus 5 available. There will be ground available. So you will always have 0 and 1 with you. If you are having 0 and 1 with you, you can implement any kind of Boolean expression. Okay, so this was a very, very important point. Very, very conceptual point. Okay. Now let's see any question. Which of these are universal gate? So this is NOR gate. First one is NOR. Certainly universal. What about this one? This is also universal only. What is the final function? A bar plus B bar. So that would be AB bar. AB bar universal. What about this one? What is this? A bar dot B bar. That is equals to A plus B whole bar. This is NOR only. What about this one? What do you think? Is this your universal gate? Let's try. A bar plus B bar and then whole bar. So what that would be? AB bar bar. So that would be equals to AB. So here in the final expression you are not getting not response. You are not getting not response. Not is not there. Inverter is not there. So this is not. Okay, just by looking at the bubble you cannot say it will be a universal gate. You need to see the final expression. In the final expression you are not getting a bar there. So that is not the final answer. That is not a universal gate. So this is not a universal gate. What about this one? A bar dot B bar. So it is A plus B bar. So this is also a universal gate. What about this one? A bar dot B bar bar. So that would be A plus B. So this is also not a universal gate because here you are not getting the response of bar. Okay, so this is also not a universal gate. So this was the concept of our universal gate. So this question came in 2022. In GATE 2022, this question came. So what they are saying, why is A plus B bar? So using instance of a D gate, basically this D gate is represented as A plus B bar. So which of the following option is correct? NAND gate can be implemented, OR gate can be implemented, logic gate can be implemented, and AND gate can be implemented. So 1, 2, 3, 4. And this is what I did in the examination because GATE 2022 was my attempt. Okay, but here I did not even check cannot is written. So these 2 options will not be there. Everything can be implemented, right? NAND can be implemented, NOR can be implemented, AND can be implemented, OR can be implemented, NOT can be implemented, XOR can be implemented, XNOR can be implemented, everything can be implemented. So I knew this thing that everything can be implemented, but what did I see? NAND, OR, NOR, AND. Tick down or fall. It costed me 2 marks. Okay, so don't do these kind of mistake. Cannot is written here. It really happened with me in the examination. I clicked on all four. So A plus B bar, this is a universal gate, so everything can be implemented. Okay, so yeah, that was the concept. So now let's see the concept of delay. Very important concept. So you have to draw the timing diagram of different digital circuits involving the elements which are having non-zero delay. So here inverter is there which is having 5 nanosecond delay, and your XOR gate is there which is having 15 nanosecond delay. For t less than 0, A was 1 and B was 0, and for t greater than 0, A is 0 and B is 0. So basically A is going from 1 to 0 and B is remaining at 0 only. So how will C look like? That you need to draw. Okay, so how you need to solve these kind of problems without doing any error? If you want error free answer, then this is the method you need to solve. So after every gate you will define a variable. So A is there. After this not gate I will define a variable, let's just say X. After this XOR gate I will define a variable, that is Y is equal to C only, but that we can see later on. So I am defining a variable from my side, right? So what is X? X is equals to A bar. So first I will draw the timing diagram of A, and then I will draw the timing diagram of X, and X is simply A bar. So timing diagram of A I have already drawn 1 to 0. So what will be the timing diagram of X? But this timing diagram is without delay. First I will not think of any delay. I don't know there is 5 nanosecond delay. I will directly draw X is equals to A bar. So without any delay, without introducing any delay, I know this is how your X bar will look like. This is how your A bar will look like from 0 to 1. Now I will check the delay. What I will check? I will check that X I will get after 5 nanoseconds. So there is a delay of 5 nanoseconds. So X after 5 nanosecond delay. So this waveform I will shift by 5 nanoseconds. So this waveform will be shifted by 5 nanoseconds. This waveform is shifted by 5 nanoseconds. This waveform is shifted by 5 nanoseconds. Now what is my second target? My second target is Y. What is Y? Y is X XOR B. I am not thinking about the delay. My target is only to make the waveform. So X XOR B. X. Now which X I will take? The delayed one. Here I will take the delayed one because new waveform I have got. No, this new waveform I have got. So delayed one I will be taking. This XOR with B. So this XOR with B. 0. This is 0. Here also it is 0, and then it is becoming 1. So till 5 nanosecond it will give me 0 only. So 0 XOR 0, 0 XOR 0, 0, 0, 0, 0. And then 0 XOR 1 will be 1. This is my Y. And this window is 5 nanosecond. This is my Y without delay. And Y with delay, what is the delay? Delay is 15 nanosecond. And Y with delay, that is 15 nanosecond, that is equals to C only. So here I will introduce a delay of 15 nanosecond. So 5 nanosecond plus 15 nanosecond. So this will go to 20 nanosecond. So this is how your C will look like. This is how C will look like. That's it. So this is the way you need to answer the problems. This is 20 nanosecond. So from 0 to 20 second, your Y will be 0, and then it would be 1. So these kind of questions can come in your examination. They can ask till what time C will remain at 0. So 20 nanosecond, and then it will be 1. Steady state value of C will be 1. So these kind of questions can come up in your examination. We will solve more examples. Let's solve this one now. Two gates are there. First one is NAND, and then there is XOR gate. 10 nanosecond delay, 20 nanosecond delay. All the inputs are changing from 1 to 0. All the inputs are changing from 1 to 0, 1 to 0, 1 to 0. ABC, ABC, ABC. After every gate, I will define a variable X, and here it is Y only. So better we should define PQ. P and Q. So first I will make the waveform of P. What will be the waveform of P? P is equals to AB bar, A into B bar, A into B bar. Okay. So 1 to 0 they are going. So initially 1 into 1 is 1, 1 bar is 0. So initially P is 0. Initially P is 0. P is 0. and then 0 into 0 will be 1. 0 into 0 will be 1. So better, like, I have to make it a bit congested because there will be 4 waveforms, right? So 0 to 1 we will go. This is without delay, but I have to introduce a delay of 10 nanosecond. So P with the delay of 10 nanosecond. So 10 nanosecond will be delayed. It will be delayed by 10 nanosecond. So it will be delayed by 10 nanosecond. This is delayed by 10 nanosecond. So this window is 10 nanosecond. This window is 10 nanosecond. So this is 10 nanosecond, right? Now, what is my Q? Q is P delayed. P delayed, I am saying, XOR with C. So P delayed XOR with C. This is what I need to do. So what will be my Q? Q without delay. Q without delay. So this XOR with C. So 1 XOR 0 is 1 only. 1 XOR 0 is 0 XOR 0 is 0 only. 0 XOR 0 is 0 XOR 0 is 0 only. And 1 XOR 0 is 1. This is 10 nanosecond, right? Now I have to introduce the delay. So this 20 nanosecond delay I have introduced. So this is the best possible method of solving these kind of problems. If you show your intelligence there, then there is high chance that you will mess it up. So do not show the intelligence, go by the method. You will be able to solve it quickly in the examination. You will not run out of the time. Okay. So 20 nanosecond delay I will have to introduce. So 0 will go to 20 and 10 will go to 30. So 20 nanosecond delay I am introducing. So this is your 20 nanosecond and this is your 30 nanosecond. So this is the waveform of Y. So these kind of questions they can ask, that for what window you will have 0 output. In Y, for what window you will have 0 output? 20 nanosecond to 30 nanosecond. That would be the answer. What is the steady state value of Y? That is 1. So these kind of questions can come. Okay, let's solve more examples. This is a big example. A is changing from 0 to 1 and B is changing from 0 to 1 but at t equals to 2.5 nanosecond. B is changing from 0 to 1 at t equals to 2.5 nanosecond. Draw the timing diagram and find the time window. Find the time window for t greater than 0 for which output is 0, or find the time as well. This can also be written. So here I will show how I will be solving in the examination, because in the examination you are not going to draw the diagrams like this. So in the examination, how I will be solving. So A is changing from 0 to 1. First I will draw the waveform of A. Roughly only I will draw. A is changing from 0 to 1 at t equals to 0. And B is changing from 0 to 1 at t equals to 2.5 nanosecond. So this is how I will be solving in the examination. Okay. Now I need to draw the timing diagram. So again, X, okay, Y is there already. So P, Q, R, there is no delay here. There is no delay. Okay. Still S, T. So P is A only, because P is equals to A only, no? A into A is equals to A. So P is equals to A, but with 5 nanosecond delay. So P is equals to A with 5 nanosecond delay. P is equals to A with 5 nanosecond delay. So this 5 nanosecond delay I can directly show. This is my P. Now here I comes. Q is A bar with 3 nanosecond delay. Q is A bar. So this is your Q. Q is A bar. So 1 to 0 it will go, but with 3 nanosecond delay. 1 to 0 it will go. 1 to 0 it will go, but with 3 nanosecond delay. So this is changing at t equals to 0. So this will change at t equals to 3 nanosecond. Are you getting this point? This will be 1 to 0 but with 3 nanosecond delay. Now what I need to do? XOR of these two. So XOR of these two. P XOR Q. So first I will do the XOR. So this is 1, this is 0. So 1 I will get. 1 I will get. Then 0 XOR 0, 0 I will get. And then 1 XOR 0 I will get 1 only. Right? And this window is 3 nanosecond. This window is 5 nanosecond. But this is without delay. So with delay I will make here P XOR Q with delay. With delay, how much delay is there? 4 nanosecond delay is there. So I will shift the complete waveform with 4 nanosecond. So from, if I am shifting from 4 nanoseconds, so 4 plus 3, this will go to 7 nanosecond, and this will go to 5 plus 4, this will go to 9 nanosecond. This will go to 9 nanosecond. Okay, 1 0 1 it is going. Now this is my R I have got. From R to S, this is simply inverted. R to S is simply inverted without any delay, because this is having 0 nanosecond delay. So S waveform I will draw, simply inverted. This is 7 nanosecond, 9 nanosecond, 0 to 1, 1 to 0. This is my S. So S and B is coming. What was my B? B is starting from 2.5 nano. B is starting from 2.5 nano, and it is going like this. So I need to XOR these two. XOR of these two. So S XOR B, that would be 0 XOR 0, 0. 0 XOR 1 will be 1. 0 XOR 0 will be 1. So 2.5 nano to 7 nano. Then 1 XOR 1 will be 0. So 7 nano to 9 nano it will be 0. Then 0 XOR 1 will be 1. Will be 1. So this we are starting from t equals to 0. From t equals to 0 nanosecond we are starting. Okay. Now what we need to do? We need to introduce a delay of 10 nanosecond. We need to introduce a delay of 10 nanosecond. So if we need to introduce a delay of 10 nanosecond, so basically all will be increased by 10 nanoseconds. So this will be the final waveform. This is my output Y. This is my final output Y. So this is how I will be drawing in the examination. Each waveform I will take, but I will keep in mind that initially I need to make the simple waveform, but I will introduce the delay. I will not forget introducing the delay. Let's check it out from the beginning what we did here. A waveform, B waveform we had. A waveform, B waveform we had. First one is simply A with 5 nanosecond delay. Simply A with 5 nanosecond delay. Then we had Q, which is 3 nanosecond delayed and inverted. Then we had XOR of these two. XOR of these two. So 1 0 1 0 0 1 0 1. So that we got without delay. Right? Then we introduce a delay of 4 nanosecond. So 4 plus 3 7 and 5 plus 4 9 nanosecond. Then S is simply inverted. It is inverted without any delay. Then B is coming here. That is this kind of waveform. Then we need to take the XOR and then delay by 10 nanoseconds. So first we took the XOR and then delayed it by 10 nanoseconds. Now for how much time it is 0? Find the time for which it is 0. It is 0 for 0 to 12.5 nanosecond and 17 nanosecond to 19 nanosecond, which implies 12.5 nano plus 2 nano, that is equals to 14.5 nanosecond. So for this much of time it is equals to 0. That's it. So this is the concept of timing diagram. This is how you draw the timing diagram. So in gate examination, if these kind of questions come, you will be able to draw the timing diagram and then tell the final answer. Okay. So no other problem is there. Now this is a short lecture only. This lecture will be of 30 minutes only. So here we studied the interesting concept of a universal gate, and then we saw how to draw the timing diagram. In the next lecture onwards, we will study about Boolean algebra. So there only we will study about Venn diagram. So in the next lecture, we will cover the Boolean algebra completely. We will see examples as well, and we will cover the theory part as well. Okay, so let's meet you in the next lecture.